two formulas for finding slopes of tangent lines. One that had the h, one that had x minus a on the bottom. And now we're going to look at the definition of the derivative, which by the way that it looks is almost identical to our slope formula for a tangent. The only difference that happens here is with all of our slope formulas, we were finding the slope at x equals 2, at x equals 3, at x equals -1, and you'd plug that in for your a value. In this one, we're going to find the general formula for the slope by just plugging in, instead of a number for a, we'll plug in x. So sometimes this formula has a, sometimes this formula has x. And when we solve for this, what we're going to get is a formula for any slope anywhere, which is way more powerful than what we were doing previously when we found just one specific slope. Oh, my highlighter is working wonderfully today. Okay, so I just highlighted what all that is. The derivative is just the slope of a tangent line at a specific point. Now, as far as language and notation goes, these are the three common ways of writing a derivative. You write f prime of x with a little dash, or y prime. These are sort of more notation like Newton would have used. And Leibniz notation, you write dy over dx, which is sort of a change in y over change of x, very similar to what you know slope is. The slope of a line is rise over run. And the main strategies are going to be the main strategies we've used for limits all the way along. We're going to use our algebra skills. Plug in the function into the definition. Simplify. Use our limit skills so that we're not dividing by 0. And then we'll be able to solve. And usually those algebra skills involve having to factor out an h. Because if you look at the formula has an h on the bottom. And if h is going to 0, you're dividing by 0. That's not allowed. If we can factor an h out of the top, that h will cancel out with the h on the bottom, and then you'll be able to evaluate the limit. So here's our first example. We've got a simple parabola. And we want to use the definition of the derivative to find the derivative, and the derivative will be a function of all possible slopes. So we start off by plugging in f of x plus h and f of x. So the difference here compared to what we were doing with the tangent ones is we're not plugging in any number. We're finding a general equation for all the slopes of all the tangents. And now we have to evaluate this limit, which is something you've been doing all the way. I think you're probably pretty good at this. Can you see that you could expand this? Multiply that out. If you multiply that out very nicely, the x squared and the other x squared simplify. Then what we're left with on top is a 2xh plus an h squared, which has an h in common. You can factor that out. And if we factor out that h, it will simplify with the h on the bottom. And now we're no longer dividing by 0, so we can apply the limit by plugging in 0 for h. And we get that the derivative is equal to 2x. Now, this is very powerful because this derivative lets us figure out the slope of any tangent line anywhere on the parabola. So in part B here, it says, find f prime of 3. Well, since we know f prime of x is 2x, just like normal function notation, f prime of 3 would just be plugging in 3, and we would get 6. What does that mean? That would mean if you drew your parabola, and when x is 3, you'd have the point 3, 9. If you drew the tangent line at 3, 9, the slope of that line would be equal to 6. So we did this with our previous formula, but now the powerful thing about the definition of the derivative is now we have a function for figuring out any slope. Like something that is intuitively obvious. Take 0, 0. It's easy to draw the tangent. It would be completely flat. What's the slope of a flat line? 0. But using the formula, we can say, what do I know about 0, 0? The x coordinate is 0. Plug it in, the slope would be 0. I can choose another point. Let's say I go to the point -1, 1. The tangent would be right here. What's the slope of that tangent line? -2, because I could plug -1 into my slope formula. Basically, what your derivative is a formula for the slope of that function. And we can now figure out the slope of any tangent line anywhere on that parabola with one equation rather than doing the slope formula over and over and over again. So this is more powerful than those slope formulas we were doing last week, because those slope formulas only gave us one point. This one gives us a function to figure out every single point possible. And so our skills at limits help us find all of these derivatives. So we're going to find y prime using the definition. We write out the definition again. And then we have to think back to our limit skills. How would we solve this limit? So again, I'll let you try it from here to solve the limit. I'll put up the answer in a bit. All right, I will put up, most of you were looking at the conjugate, multiplying by the conjugate, and then on the top we would multiply it out. On the bottom we would leave it factored because our goal is to get rid of that value of h. And what's really nice on the top is once you distribute this 9 in here, you're going to get 9x plus 9h minus 9x, and the 9x's will go and cancel each other out to just give you 9h on the top, which is really nice because at this point you'd be allowed to simplify that h. And now we no longer have that single h on the bottom, which was causing us problems. You can now plug in 0 for h, and you get 3 root x plus 3 root x on the bottom, which is 9 over 6 root x, which you could write as 3 over 2 root x. And for those of you that already know calculus, you'd be like, or you could change, you know that you can change a square root to an exponent of a half? And if you moved an exponent of the half from the bottom up to the numerator, you would get an exponent of the negative a half. So these would technically be equivalent, but the green one seems like, why would I change it to that? Okay? And on average, how long did you think this question took us? 15 minutes? That long? Okay. A few. Okay, so like, I don't think it was 15. But yeah, a few minutes, maybe 5 minutes, 5 or 6 minutes. I'm going to tell you that if it took you 5 minutes, we are going to learn skills in this class that in this question will shave off 4 minutes and 55 seconds. Okay? Which is crazy. A crazy difference in speed, right? That would be like next year they discover something and say, you now only have to go to school for 2 years to graduate from high school. Right? How long have you guys been in school? 12 years? Would that make you mad if next year they say, no, we've developed new technology, kids can graduate after grade 2, they will know all the same stuff you did? That'd be like, blow my mind. Okay, so, well, I guess that one doesn't want to disappear. Next question. Maybe. Let's see how long this one takes us. dy dx, we're going to find the derivative if y equals 2x cubed plus 4x. So what we need to do is take the definition and plug that into the definition. And this I want you to do the first step on your own. I'll come around and help. So take the definition of the derivative and plug this in. In started part, so if we were plugging in, right, the definition of the derivative, which I'll write up here, limit as h goes to 0, of f of x plus h minus f of x over h, for f of x plus h, just so that you can visualize it, I'll put that in green brackets here, and I'll put green brackets there. F of x plus h means wherever you had an x, you're replacing it with x plus h. So I had 2x cubed plus 4x. I now have 2x plus h cubed plus 4x plus h. And then in purple brackets it says, I'll put purple brackets around that, minus f of x. Then we subtract what f of x was originally. Now starts the not very fun part as Aiden is shaking his head. Okay? Everything is pretty much okay except for the x plus h cubed. I'm going to do that off to the side. X plus h cubed means x plus h times x plus h times x plus h. How do you multiply 3 things? You multiply 2 of them, get an answer, and then multiply again. Okay? So I could multiply these 2 together and get x squared plus 2xh plus h squared times by another x plus h. And then I could distribute all of this, x times x squared, x cubed. X times 2xh and an x squared times h. I could draw all the arrows. Okay? And then if I simplified, I would get which some of you might remember from grade 12 pre-calculus if you've done the binomial theorem, that you could use the binomial theorem or Pascal's triangle to figure that out. Is that what you're going to mention? Yeah. So if you look at the coefficients here, 1, 3, 3, 1, if you've done Pascal's triangle, those coefficients could come from Pascal's triangle. And we could use the binomial theorem to expand that quicker. If you haven't done the binomial theorem yet, then you just have to multiply it out like we did here to simplify and get the answer. So after multiplying x plus h cubed out, and I get x cubed plus 3x squared h plus 3xh squared plus h cubed, I can go back to our question here and plug that in. Meanwhile, I also distributed the 4 to 4x plus 4h, and then I distributed the negative sign to negative 2x cubed minus 4x. And from here, you're going to have to gather like terms, see if you can get that h to cancel out. Yes. So you're dealing with and having to work with a lot of data. That's good. But you no longer have to write the limit. Once you plug it in, you don't write the limit. Four. So at this point, if I distribute my 2x cubed, this part here would cancel out with the minus 2x cubed. And this 4x will cancel out with this minus 4x. What am I left with then? I have 2 times this, 6x squared h, plus 6xh squared, plus 2h cubed, plus 4h. And each of those has a common factor of h in it, so I can factor that common factor of h out. Again, this has been our goal all along, so that these h's will simplify. And once that h is simplified, you can now evaluate this limit by plugging in 0 for h, and all you'd be left with is 6x squared plus 4. So again, that took us about 5 minutes, and we'll be able to shave off 4 minutes and 55 seconds, maybe even more on this one, to get the answer, which is quite powerful. So again, what does this mean? Okay? Do you know what the 2x cubed plus 4x graph looks like? I hope not. I'm going to pull up right now. Let's see if I have it here. No, it looks like it's not. I'll see if I can get it ready for next class. I was going to graph it for you and show you what the derivative looks like. Okay. Another one to try. Try plugging in the equation. I'll help you with the notation. Did it make sense? Yeah? Okay. We'll figure that out. There's more than one law. So the crazy thing about this one is just the sheer amount of algebra that you're dealing with. And then once you have the top as a single fraction and you combine your like terms, you can think of this as h over 1 in your denominator, and you have a fraction divided by a fraction is same as multiplying by the reciprocal, and your h's simplify. And they go away, and that's our whole goal, because now you can plug in 0 for h and get negative 5 over 2x minus 1 squared, and if you had multiplied out the bottom, that's fine as well. So what we find in the calculus course is it really, really will strengthen our algebra skills, because you're going to have to deal with a lot of algebra all at once, holding a lot of data, controlling that, and being able to simplify as you go.